Hi, I'm Tom from the Software Architecture Group. Our paper is titled Structured Editing for All, Deriving Usable Structured Editors from Grammars. So, structured editors have been around for a long time. Among the reasons people use them is that they prevent syntax errors, they allow for direct manipulation of syntax nodes, they allow for a seamless composition of languages and to mix code with specific notations. If we compare structured editing to text, we notice that in the first stage, we are just editing on a long array of characters, and only later we obtain the structure through a parser that interacts with whatever the grammar is of what you're interacting. This is in contrast to structured editors, where we have a handwritten specification for how interactions should occur, as opposed to interacting with just general purpose text interface. So while this yields incredibly usable and nice interactions for the specific editor, they do not generalize as easily. So the question that we set out to answer was, how can we keep the usability of handwritten structured editors but make them available across languages? And our approach to this is to introduce an input reconciliation process that acts on the meta level, on the grammar itself. So we're still handwriting interactions, but we're doing it for grammars as a concept rather than a specific grammar, a specific editor. Meaning, in the end, we get usable interactions across all languages that have a grammar. Now for a quick demo, you can see here first I'm clicking for the first time on a Rust file and I'm pointing it to a Rust grammar, which will now be downloaded and imported, and I can get started typing in Rust in this editor. A little more zoomed in example of the actual editing process now in TypeScript. I'm starting to type, and as soon as the editor can tell what I want to type, it auto-completes it. And you can see I'm adding a type annotation, now an equal sign, which will jump into the right position according to how the grammar is structured. And you can see now, as I'm adding additions, that these are also nested according to the associativity. And now I'm finally changing the let binding to be a const binding. So how does this work? We have here an excerpt from the JavaScript grammar and the 2 plus the identifier a as an example here. If we take this apart, we can see that it consists of a set of blocks as well as text field, corresponding roughly to the terminals and non-terminals in the grammar. But in addition to just this information, we also store pointers back to the original grammar that inform each individual block how edits can occur and what sort of valid edits are possible in its context. This is then realized in this input reconciliation process. Here we are looking at the specific process for character entry. The idea is to always locate the closest possible insertion point for a given change. So in the simplest case, if we are in a string and we're getting the input a, we can just simply insert it here in the string because it still satisfies the regular expression for that text field. Next, if that is not possible, for example, if we are in a 42 and receive a plus sign as the input, we have to reparse it. So we take the 42 and the plus and we ask the grammar what could take the 42's place here, and find that indeed a binary addition can work here. If this also fails, for example, if we're on the plus sign and we're adding an equal sign, then we're currently a binary operator, but we're actually stringifying, meaning we remove the meaning of being a binary operator and ask it to reinterpret it because the previous things did not work out, the previous steps, and find that indeed we can turn the pieces that we have obtained into an augmented assignment instead. If this is also not possible, for example here when we inserted number 2 onto the closing parentheses, we look to the right and try to locate the next insert position in the grammar, for example an optional field or repeat, and expand it here into its own number block. Finally, if we try an input in a place that all of the previous steps does not work, for example, adding a plus sign here on the 3, which is forbidden by the grammar associativity because they cannot appear on the right-hand side, we try the entire process again, but on the parent, and find that indeed the rub step is allowed on the parent, leading us to this binary addition here that surrounds the inner. There are other aspects like how to resolve ambiguity that you've also seen in the demo video, and a similar process that happens for deletion, which we documented in the paper. For our evaluation, we performed a user study with the goal to perform simple edit tasks in 3 different languages and find out how people perform. And we had 18 participants with varying degrees of programming experience run through the experiment. We started with an introduction in Python, a 5-minute tutorial, and then some warm-up tasks, and then the 3 different languages, each performed once in our editor, Sandblocks, our implementation of the input reconciliation process, and a baseline text editor, and these were balanced using Latin Square. The first thing we wanted to find out was whether editing felt natural to users, which they tended to agree with a median of 6 out of 7 on the different dimensions we asked them for: editing, deleting, and navigating. Second, in terms of usability, we wanted to find out how the editing speed compares to text editing, and found that we are getting close, but are still by a factor of from text editing between 0.8 to up to 4.2 for individual users. Finally, in terms of availability across different languages, we demonstrated this as part of our setup, where we only gave users a tutorial in Python, and the actual experiment was conducted with JavaScript, Clojure, and regular expressions, and users could use these editors, these languages, without any issues. So to conclude, our implementation Sandblocks of the input reconciliation process allows to derive structured editors from grammars. The process itself yields usable text-like interactions, and as such brings structured editing to all languages representable by a grammar. Thank you.